You would agree that building something new is always interesting as well as challenging. In today's topic, let's look at a concept that helps us in building something new, maybe a new product or a new service or even a new process. We will look at a design approach that not just can help to create a capable process that meets customer specifications, but also keep the process means centered at the target always. If you have experience in process designing, you would have guessed we are talking about something to do with the robust designs. Today we will go through a concept called Taguchi's designs, which is very useful in robust design situations. Situations where factors are too many, where noise factors have got significant impact on factors and the output response. Since you have picked up this video on Taguchi's method, I would go with an assumption that you are exposed to quality and the operational excellence concepts like Six Sigma, design of experiments, etc. Intent of this video is to introduce you to the concept and its application. So what we have done is we have made this tutorial in 3 parts. It would be advisable to go through all the 3 parts at your pace, but in that order. So it will make the understanding much easy for you. Before we get into the specifics, it's important to understand how it helps to spend a good amount of time on new product or process design. Whenever something new has to be started, the how part gains significance. How do we start? How will we do this? The people respond to this anxiety in 2 ways. Either they believe in starting light and evolve as they make progress, or they believe in getting it right the first time. In the first category, how to do or how to work guideline comes from the experts. Through practice, trial and error, over a period of time, process becomes efficient. At times, in the initial period, breakdowns can be there, escalations can be there. In the second category, the experts come together to scientifically design a new process that will meet the requirements of the customers and the business from the beginning. It allows to integrate the best available technology or practice right at the start, as all positive and negative effects and their causes are systematically analyzed. Yes, it consumes time, but then it guarantees a satisfied customer, efficient way of working, doing more with less, faster ROI, and obviously a differentiating brand value. So both have their ups and downs, and the choice is made by the business based on their priority at that point of time. For the purpose of this video, we will spend time on the second aspect. That is, let's try to get it right the first time. Speaking about the elements of design that make it successful, the most important piece is how well we understand our customer and the market. What will delight them? How will we have to realign our process to always deliver what they need? Then we have our business which exists for our customers. So in our business, what is our vision, our goals? Are customer requirements going to drive a positive change for our business? Any business is an aggregation of various business processes. If process is reliable, then the business outcome would be dependable. So what do these customer and business requirements, or what we call as CTQs or critical to quality parameters, mean for a process? What has to change in the process to bring improvements in these CTQs? Which parameters should change? At what level should the process parameters operate? These are very important questions for which we need to find answers in our design journey. Once we are clear about these input parameters, the next important task is to find a quantified relation between what needs to be improved and what needs to be strictly controlled to bring in these improvements. This relation is referred to as the transfer function. Design of experiments, simulation, these techniques are few scientific methods that help in arriving at this transfer function. The next important part is to know the operating limits for the factors that influence the process output Y. Variation and its impact on these factors is studied to assign appropriate limits to these factors within which we need to control them. Even after doing all this, there are certain factors like the environmental factors, the temperature, humidity, or even the customer usage pattern, which we cannot control. But these factors will influence the performance. So we need to minimize the effect of such noise factors. That's when we get an optimal transfer function with the right factor levels that is best for the output parameter. When the product or the process is designed as per these quantified factors at their optima, the reliability in performance would flow back to the business and to the customer. Now, this is in essence what goes into designing a new process or a product. So to summarize, process design is all about evolving the best transfer function to relate the CTQs, or what we call Y, with controllable factors or the X's, while process optimization is all about finding the optimum factor levels for peak performance. Let's quickly run through some techniques which are used in process design and optimization. The most common is regression. Commonly, it is used to find a transfer function between Y and X's, or finding the vital X's that represent the Y or the output response. From a design point of view, one limitation is that it does not confirm causation between Y and X's. It can be used if experimentation is ruled out and we have to rely on data mining. Design of experiments, or DOE, is the most precise method to shortlist the factors or X's based on causation and to determine the transfer function between Y and X's. It traditionally uses a series of random experiments conducted at different levels of the factors to model Y as a function of X's. It being so detailed comes with a huge investment in terms of time, effort, and cost. Now, once DOE, or the design of experiments, provides us with the vital factors plus a model function between Y and X's and their favorable control levels, we use the optimization designs to find if there are better factor levels of performance for Y or the output response, or to determine the best operating levels for the factors. This method is known as response surface method, or RSM, and uses techniques like ascent descent or simplex for two-level optimization, or a central composite or a box Benkin for a three-level optimization. But when the need is to have a process so robust that the process mean not just stays within the specifications but also is always centered at the target, Taguchi's designs are very useful. The underlying belief in this approach is that every time a process moves away from the target, there is loss to customer, even if the process is within the specs. Now, this method attains the robust design by modeling not just the controllable factors as we do in conventional design of experiments, but also considering the noise factors. We had been talking about these noise factors. What exactly is a noise factor? So let's take an example. Let's say we are designing a printer. One of the noise factors would be the paper type. As we do not have any control on the paper type, that will be used by the consumer, and it does impact the print quality. So this method allows us to conduct experiments at different levels of the noise variables to factor in their impact and then accordingly design the product. So in this video, we'll walk through the Taguchi's method to learn how this technique is used in creating robust designs. Every concept has got a core belief on which its methodology is built upon. Taguchi's loss function drives the objective of the Taguchi's design. The objective being to design a process that not just complies to the customer specifications but also maintains the process mean at the target. According to Genichi Taguchi, every time the process deviates from its target, there is loss to the customer and producer. Larger the deviation from the target, larger is the loss. This quality loss is proportional to the square of the deviation of mean from the target, shown as t here, where y is the process mean. The function has m by d as a constant, where m is the monetary loss to the producer when process goes beyond the specs, and d is the tolerance, where about 50% of the customers view the product as defective. Now this quality loss is not just due to the deviation from target, but variation in the model also plays a significant role in this. So if QA is the average quality loss per unit of the product in a sample that follows a distribution whose mean is given by mu and standard deviation by sigma, then QA is proportional to the sum of square of the deviation of mean from the target and the variance. Now looking at the quadratic loss function for Taguchi's designs, here we have a process at mean, mu and standard deviation sigma. The effort in a robust design is to ensure that this mean is always aligned with the target. Conventionally, when our process output goes beyond the defined specifications, we tag that output as defective. But in case of Taguchi's designs, whenever the process output deviates from the target, moves away from the target, there is a loss to the customer. So it's important to understand how the core belief of Taguchi's designs differ from the traditional design methods. Traditionally, what we believe is when the process output is within the specs, process is capable to meet the customer requirements. Only when it deviates beyond the specs, the defects occur and customer is impacted. But in Taguchi's designs, quality is when the process output is at the target. Every time process mean deviates from the target and there is variance in the process, quality loss will be there. That's why Taguchi's method follows an approach which minimizes the impact of variation on response, neutralizes the impact of the noise, and thus ensures process mean is at the target. In conventional design of experiments, we model the response, that is y, on controllable factors which we call x's. We block the noise factors during experiments in DOE. But in Taguchi's designs, we model the response y on controllable factors and noise both. This is what leads to a robust process centered at the target with minimal influence of variation on the factors as well as response. Now that we have a high-level idea on Taguchi's designs, before we dive deep into the methodology, it is important to understand when can we use this method. Now, one of the significant advantages in this method is that it reduces the required number of experiments which obviously reduces the time and cost of experimentation. In the traditional design of experiments, if we have, let's say, 6 factors with 2 levels, we have to do 2 to the power of 6 experiments. That is 64, and with replicates it will be 64 into 2, that is 128 experiments. Even if we choose half fractional factorial design, we will end up doing 64 experiments with replicates. Whereas in Taguchi's methods, we need only 8 experiments. The second most useful situation is when the noise factors have significant influence on the control factors and the process performance. In Taguchi's method, the design is modeled on both controllable factors and the noise factors, and hence will return a robust process. As a rule of thumb, the number of control factors should be greater than the number of noise factors, as only then we will be in a position to locate a factor that will help reduce the noise. The other very important aspect is when any deviation from the target will invite major tangible losses for the business, for the process, then we definitely need a robust design approach like Taguchi's method. Now, in the set of beliefs in Taguchi's designs, few can be seen as limitations about the approach. And as a practitioner, it is important to be aware about those limitations. Number one, this method doesn't believe in randomization, so to say. The concept of lurking variable, which is an unknown variable that may impact the response, is handled by randomizing the experiment in the traditional method. Taguchi feels that the users must be expert in their processes, and all such lurking variables must be known beforehand. Number two, it believes that the user's experience and in-depth knowledge will help to identify the interactions and will help to choose the significant interactions before we start the experiment. So this method must be only used when we have the subject matter experts who are willing to devote the required time on the project. This is very, very important. In some cases, it is not the optimal best we are after when it comes to the process output. Especially in a product scenario, at times we want the output to vary in a controlled way when an input factor is changed. As an example, if we take the accelerator pedal in a car, now in the car we would want the rate of acceleration to be tied to how much we press the pedal. Now such a factor is called the signal factor. So here we are referring to the accelerator pedal in the car and the depression that is going to be put on that pedal. That forms the signal factor. And the response, which is the rate of acceleration, should be in proportion to this depression. So in such cases, Taguchi's designs can be very useful. In practice, we see the application of Taguchi's method in two scenarios. One, when we want to find the optimal levels for input factors that can provide us the best level of output response. Such a level would be a fixed level, like in a silicon wafer design. We would want a process that precisely coats a specific thickness of silicon layer on the wafer. This scenario calls for a static response design. The second scenario, like we discussed earlier, a case where we want to optimize the relationship between the output response and a signal factor. So here the response is not at a fixed level, but will have an optimum operating range within which it ought to be efficient. Like the rate of acceleration we spoke earlier, even the brake performance and its relation with how much the brake pedal is depressed is a similar case. So such scenarios call for a dynamic response design. We'll walk through each of this method in this tutorial. Now, whether we adopt a static or a dynamic method, Taguchi's method goes through three stages: the systems design, the parameter design, and the tolerance design. Systems design, it is all about effectively defining the problem, effectively defining the vital design factors and their levels. So this stage requires experts who have in-depth process and engineering knowledge. The parameter design, it's all about conducting the experiments and identifying the optimal settings for the design factors. Now, ideally, the design work should get completed by the end of the previous stage, that is the parameter design stage. But sometimes we would not be able to attain the target response quality after the parameter design. Then we need to determine tighter tolerances around the optimal factor settings that we have identified during the previous stage. This is what happens in the tolerance design phase. So on one side, it leads to a robust design in which the designed process delivers at the target and is least impacted by the variance or the noise factor. But on the other side, it increases the cost, as practically, if we have to achieve the tighter tolerances, we need better product or the process components. Every ideology that way comes with certain key concepts and terms, which must be very clear to the practitioner. And same applies to Taguchi's designs as well. So let's start with the orthogonal arrays. Now, if you have used design of experiments, you would know about a property called orthogonality. This property is key to Taguchi's designs. Taguchi's design uses something called orthogonal arrays, which was introduced by C.R. Rao. It helps to reach the optimum levels with minimum trials at minimum cost. Now, looking at some basic definitions, starting with orthogonality, let's say we have x and y as two vectors. Then we would call these two vectors x and y orthogonal if the sum of their dot products equals to 0. That is, x1 into y1 plus x2 into y2 up to xn into yn. The sum of all these terms equals 0, then we would call the vectors x and y as orthogonal. And if these two vectors are orthogonal, they would be mutually perpendicular as well. Now, coming to an array, it would be called orthogonal when it is balanced by considering all levels of all the factors equally distributed in the array. So, we can say that the orthogonal arrays are balanced designs that belong to the family of highly fractional factorial designs. Now, to understand an orthogonal array, let's consider two factors, x1 and x2. Now, both factors have two levels, one high and the other low. High is represented here as 1 or plus 1 and low as minus 1. And this array or the experimental layout is said to be orthogonal if all the levels for all the factors are taken for experimentation equal number of times, which means we have got two factors here, x1 and x2. Both these two factors have got two levels, 1 and minus 1. So if we try to consider the number of pairs that we can make out of this 1 and minus 1, we would say that okay, the pairs can be 1 1, then we can have 1 minus 1, we can have minus 1 1, and then finally we can have minus 1 and minus 1. So these are the pairs that we can make out of the levels 1 minus 1 for two factors. And if all these combinations are present in an array, representing two factors at two levels, then that design or that array is orthogonal, which we will see here that all those four pairs are being used in this array. So that way this array qualifies as a orthogonal array. We can also check the property of orthogonality that we defined earlier. So in this table, if the dot product of all the levels of all the factors add up to 0, then the property of orthogonality would be upheld in this example. So in this case, the first run has factor 1 at level 1, which is the higher of both the levels, and factor 2 also at level 1. And the product would be 1 into 1, which is 1 here. In the second run, factor x1 is at level 1, whereas factor x2 is at minus 1. So the product becomes 1 into minus 1, which is minus 1. So that's how similarly we get minus 1 and 1 in these remaining two runs. And finally, if we add up the terms in the last column, we see that we are getting the dot product of xi and xj as 0. So that basically qualifies this array from an orthogonality point of view as well. Now, the main advantage of this orthogonality is that each factor can be evaluated independently without the influence of other factors. So, orthogonal arrays help us to represent the controllable factors and the noise factors in an experimentation layout. To understand this in more details, let's have a look at a simplified view of how an experimental layout will look like after choosing an appropriate orthogonal array. So let's say we have to study how much a wire heats up when electric current is passed through it. So as a part of the system's design, we carefully identify the design factors. Let's say the factors include the wire diameter, wire length, the material the wire is made up of. Let's say ambient temperature has an influence on heating, but since it cannot be controlled during the actual process, it becomes the noise factor in this case. The factor levels are also selected carefully as we have shown here in the table. Now, the design factors or the controllable factors with their levels, they form the inner array in case of an orthogonal array. The objective of the experiment is to find the optimum levels for these factors, the factors which are there in the inner array. The noise factors, on the other hand, they are in the outer array. The noise factors influence the response, but as we said, they are not controlled during the use of the product. Like the example of the printer that we took some time back, where paper type was considered as a noise factor because it's not possible to control which type of paper is going to be used by a customer. So care has to be taken while choosing the levels of these noise factors. The levels should ideally represent the range of conditions which will exist in normal product use, and the experimental response will be noted for each of the noise factor level as shown here in this case. And this is the general representation for orthogonal arrays, where S is for the number of levels for each factor, K is for the maximum number of factors whose effects can be estimated without any interaction, and N is for the total number of trials during experimentation. So if we take some examples, like in this case, L8 orthogonal array can handle 7 factors at 2 levels by conducting 8 experimental runs. Similarly, L18 orthogonal array can handle mixed levels, 1 factor at 2 levels and 7 factors at 3 levels by conducting 18 experimental runs. The table here shows a standard view of the list of orthogonal arrays available in Taguchi's designs. In the coming slides, we'll see practically how do we choose a specific array. The columns in this table represent the array notation that we saw on the previous slide, like the number of experiments to be run, maximum number of factors a specific array can handle, and the various factor levels that are explained by a specific array. Like for example, if we take L8, we can see L8 here in the third row. So it says 8 experiments and the design can have maximum 7 factors at level 2. After orthogonal arrays, the second most important concept in Taguchi's designs is the linear graph. It helps us to visually represent the factors and interactions, which in turn helps to understand how do we allocate the factors to the different columns of the array. We know in experimentation, certain tasks are quite difficult as well as equally critical, like for example, to decide which factor at what level should be considered with other factor levels in the experimentation, to decide how many such experimental runs would be adequate, to decide in what order these runs should be. Now these tasks are one of the most critical yet quite difficult in any of the experimental methods. In conventional method, we rely on the in-depth subject matter knowledge of the experts in deciding upon the factors, levels, runs and their order. In Taguchi's designs, this task is simplified using the linear graphs. A linear graph, so to say, visually represents a set of factors and their mutual interactions. These factors and interactions are then represented as columns in the array. The linear graphs are standard for each array, like for L8 orthogonal array, these are the 2 linear graphs. These nodes 1, 2, 4 and 7, they represent the main factors, while these edges 3, 5 and 6, they represent the interaction between the main factors. Like this edge 3 shows the interaction between the factor 1 and 2. This is the interaction between factor 1 and 4. Now if we take a case, a specific design case, where we have to study the main effects of 4 two-level factors, let's say the factors are A, B, C and D, and the interactions between AB and BC and AC in an experiment. So in that case, we will use linear graph 1, this one. So the nodes of the linear graph will represent the factors, like 1 can represent A, 2 can show B, 4 can be C, 7 can be D. And the interaction between A and B can be shown by 3, interaction between A and C can be shown by 5. But if in the same design we have to study the main effects of the factors A, B, C, D, but when it comes to the interactions, now we have to study the interaction of the factors B, C and D with one factor, that is A. So basically we have to study the interactions AB, AC and AD. So in that case, we use the linear graph 2. So if this is the way we would represent our factors in the linear graph, now coming to this table, we can see how the factors are going to be allotted to each of the column of the orthogonal array. So factor A goes to column 1, B to column 2, factor C goes to column 4, D goes to 7, and the interaction A and B would be confounded or shown using the column 3 interaction BC by column 6 and AC by column 5. So in the first video of this series, we got introduced to what goes into designing a new process or a new product. We looked at how Taguchi's design has a core belief that is different from the traditional view. We said that in Taguchi's designs, if the process mean deviates from the target, customer and producer start to incur losses even if the mean stays within specifications. We looked at the static and dynamic response designs and understood that the Taguchi's design goes through 3 stages: the systems design, the parameter design, and the tolerance design. We looked at the orthogonal arrays and its notations. We understood the relevance of linear graphs in selecting an experimental layout. So this first part is more like a handshake with Taguchi's designs, where we have now got introduced to the concept. In the second video of this series, we will look at few practical cases with different factor levels and interactions, where we will learn how to use orthogonal arrays, how to use the linear graphs, and we will get introduced to a new term called signal to noise ratio. I hope this introductory video on Taguchi's designs was useful. To get a complete hang of this topic, do watch the second and the third part of this video series. Keep watching this space for more interesting videos from the process design, re-engineering and improvements space. You can subscribe to the page and keep receiving updates as and when we upload a new tutorial. In case you want us to talk about any specific concept, feel free to contact. The contact details are mentioned here on the slide as well as on the page. So good luck and happy learning.